Hello everybody, I am making this video just in case I'm not able to make it into class. I am out of town because we are on spring break vacation and hopefully I'll be in class, but I will definitely be in a car, so I'm just recording ahead of time just in case it doesn't work in the car. So this is my final project. I decided to do a chemistry unit on gases. This is actually a unit that I just finished teaching before, actually just this last week we took a test and everything. But I tried to kind of make it more modeling-esque as I was doing it over the last month. There are some things that I definitely need to change and improve for next time, and so I've incorporated some of those changes kind of as a plan for next year based on what we've been learning in class. So let's jump right into it. So starting out the unit, just getting oriented, I would plan on just doing a quick discussion. It says discussion like this is a long drawn out thing, but this could be just like a 5-minute intro to just talk about, okay, we're going to learn about gases. Let's get our brains kind of rolling and think about what, if as a chemist, what could we measure or observe about gases? And so we could talk about some qualitative properties of gases that we could investigate, such as the color, the odor, whether it's toxic or dangerous for human consumption or anything like that. And then we could talk about maybe some quantitative properties of gases. And so this kind of leads into kind of the big four properties of gases, characteristics of gases that will eventually lead us into the ideal gas law. So just kind of getting oriented with, okay, what do we want to know about gases and what can we know about gases, I think helps get us in the right direction. And so then what this could do is this could lead into some whiteboarding activities. I did this first one with my students, and I thought of a couple others that I could do with students at the beginning of the unit just to kind of, again, see what they're thinking. What do they think about gases? What do they know about gases? How are they conceptualizing this topic? And so so when I did this first whiteboarding, how or why do gases exert pressure? Basically, I showed them a balloon and I said, okay, well, if we look at all the particles, if we consider all the particles in this balloon, the total volume of the particles themselves is teeny tiny. And yet somehow this balloon is this big, but the actual matter in the balloon is only taking up a teeny tiny volume. So why is the balloon so big? Maybe I gave them too much information to start with because I'm telling them how much matter is actually in there. But basically just trying to get them to think of like, how does gas pressure even work? And so that was a good whiteboarding activity. Lots of interesting ideas. Some of them wanted to bring in the idea of like reverse intermolecular forces, which I thought was really interesting when we did this. They were like, maybe there are repulsive forces between the particles that is pushing them apart from each other and making the balloon expand. And so that was interesting to talk about. But other things that could kind of go along with this. Why does a balloon expand in a vacuum chamber? So I actually just recently discovered I have a vacuum chamber in my room, which is really exciting. And so we were playing with that. And so if I put a balloon in a vacuum chamber, suck all the air out around the balloon, why does it expand and fill it? Interesting. Another demo I've thought about doing but haven't done in class is just, getting a metal gas tank. And I've done this personally, but I haven't done it for my classes. Like if you just empty it out really fast, it like frosts and gets really, really cold. And so why does releasing gas from a gas tank lower the temperature? So these are some other potential whiteboarding activities that we could do just to kind of get a sense of like, there's some interesting things that gases do that we want to figure out. And so this is kind of my idea of introducing the unit. So then from there, we would start developing our model. And this is something that I've done the last couple of years, and I really enjoy it. I use the virtual lab on PhET, P-H-E-T, PhET, to help students kind of derive the 4 simple gas laws. So instead of me, again, getting up and just telling them, these are the simple gas laws, they can kind of figure it out. Now, if I had lab equipment and the ability to do this in person in the actual lab, I think that'd be really cool. So that's why I put virtual in parentheses. But this is just kind of an investigation of, okay, let's actually figure out how volume, pressure, temperature, the amount of gas, whether it's moles or mass, How are all these things related? And let's just break it down into simple, two variable relationships. Okay, so we would investigate Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. So these are the simple gas laws, and I've had good success with this lab of having students. Basically, I just have them change. So like if we're investigating Boyle's law, they just change one of the variables 10 times and then write down how it affects the other variable. So they're basically just finding like coordinate pairs, and then I have them graph 10 data points of, okay, I have these 10 pressures and I had these 10 volumes to go with that pressure. And so what does my graph look like? And then from the graph, we basically determine whether we have a direct relationship or an indirect relationship. And so I find that to be a fun way for them to kind of discover or figure out the simple gas laws for themselves. Now, this can lead into a conversation and some activities about quantitative reasoning, which we've talked about in this class. I did not do this in this unit, what I'm about to get into, and it was very, very, very apparent to me based on how students were asking questions before the test that our quantitative reasoning for some of my students was very, very weak and almost non-existent in terms of thinking in proportions, thinking if I change one thing, how does the other thing change in a ratio relative to that? And so one thing that I think would help is, yes, in the virtual lab, we would derive the gas laws and have a graph, but then I think I would want to have a follow-up activity where we would actually look at the graph, and then I would try to explicitly ask questions of like, okay, let's think in ratios. If I double the pressure, what happens to the volume and in terms of a ratio? So we could be like, oh, if the pressure goes from 1 atmosphere to 2 atmospheres, what happens to the volume? And you might say like, oh, the volume went down. But trying to just explicitly like look at graphs, make graphs, and then get them to talk about it in ratios. And so then another thing that, so then that's where for every statements I think could be useful of, okay, let's reflect on our graphs. Let's reflect on these ratios, or these relationships in terms of ratios, instead of saying like, oh, it went from this number to this number and this other thing went from that number to that number. I don't think students naturally put together the proportional reasoning. So that's something that I would want to include for next time. And then also another thing I think would help would be to have them draw diagrams of saying like, okay, if I double the pressure, let's draw a diagram of what doubling the pressure looks like on a gas, whether it's a movable piston or a balloon or something like that. And then show the volume going to half its volume, something like that. Or if I double the temperature, let's show the thing expanding. I think that would help them cement the proportionality of the simple gas laws. At the end of this unit, I had some students who were like, wait, so if I increase the temperature, what happens? And what happens to volume and that? And they can kind of intuitively figure it out that like, yeah, if I heat something up, it expands. Like that's just kind of common experience that they have. But I think drawing the diagrams would help cement the relationships between these variables of which ones are directly proportional and which ones are indirectly proportional. So I think this helps kind of put together a quantitative understanding of how all these variables relate to each other. And then from there, we could put them all together and we get the ideal gas law. And I stole this little graphic from Wikipedia, which I happen to like. I like how it shows the ideal gas law, but then it highlights the simple gas laws in it just to kind of help us visualize how everything works together. So this is kind of a nice kind of summarizing graphic for all those relationships. And then for those of you that are curious, instead of lowercase n, it has capital N, which is the number of particles as opposed to the number of moles. And then because you change that unit, instead of the gas constant, you have the Boltzmann constant, which I guess is just the gas constant divided by Avogadro's number, something like that. Anyway, I had to go look that up. I'm like, why is it KB instead of R? But it's because we're dealing with capital N instead of lowercase n. But anyway, that's a side note. We're going to move on. So students have developed the model, their understanding of how these relationships work. I have some quantitative reasoning. I have some diagrammatic representations, as we might say, of these simple gas laws. And so now I have some activities that where students can kind of deploy their understanding in kind of a hands-on sort of way. And so this was an activity I had my students do in this unit in this last month, and it was really fun where I kind of skipped over the part of asking them if they think gases have mass. I kind of just assumed that, and then they were asking me questions like, wait, do gases really have mass? And I was like, dang, if we're asking this question, then we should probably do an investigation. So I just told them, you prove to me whether gases have mass. And so I ended up tweeting this, but my students came up with lots of fun activities or demonstrations to prove that gases have mass. So just very simply, you take an empty balloon, you take a blown up balloon, and then you weigh them, and hey, there's a mass difference, and the only difference is air, which is a gas. I had Sudas measuring a closed soda can on the balance, and then opening it, then letting the air out, and then they put it back on the scale, and what do you know? The mass is different. And so fun stuff like that where they can prove that gas has mass. So that's just kind of a conceptual thing. Another fun one that I thought was kind of cool, some of my students enjoyed it more than others, is basically I just gave them an empty balloon and said, put 6.022 times 10 to the 23 gas particles in this balloon. And so what essentially I'm challenging them to do is think about the physical environment they're in. What's the room temperature? What's the atmospheric pressure in this room? We just assume 1 atm because I don't really have a barometer that I could use. And then assuming pressure, measuring temperature, and then if we assume that the balloon is a perfect sphere, we can then get volume from there. And so we can basically use the ideal gas law to then calculate the number, and then we assume 1 mole, calculate the volume that the balloon should be if it were to be filled with a mole of gas. And so there are some assumptions that go into there that are not entirely accurate. I think the balloon being 1 atmosphere and it being a perfect sphere are not exactly accurate, but the point is that they're applying the ideal gas law in kind of a real sense, and it's kind of disorienting for them because instead of me giving them a nice, neatly worded worksheet that's like, here are all your variables, please plug them in and solve the equation, I just give them an empty balloon and say, do this thing, and I word it in a disorienting kind of way of put this many gas particles in it. It's like, what? How do I count gas particles? But I'm just trying to give them an opportunity to apply what they've learned and then kind of puzzle their way through to the conclusion on their own without me holding their hand. So that was that. And then, of course, I don't know, calculations, condition changes. So I don't know, that's just a fancy way of saying we're going to do worksheets and practice what happens if I change the pressure, what happens to volume. If I change the temperature, what happens to pressure. If I change the amount of gas, what happens to the volume, like just doing calculation problems. And so I think that's also part of how practice works is you practice doing the math. And so whether you grade those worksheets or not, if you're doing standards-based grading or not, I guess depends on the situation. But we all agree, I think that students should be practicing their math skills. So that's just what I mean by calculations. And if I change conditions, before and after, that's what would happen. So based on that, I am hoping that from these experiences that my students should be able to explain some things verbally to me. They should be able to explain, for example, how gas particles are physically arranged in a sample. So this goes back to some of the whiteboarding stuff that we talked about at the beginning of the unit of why do gases exert pressure? Why are the particles so spread out? How do they move and things like that? And so how do gas particles move? So this is kind of tying back to conversations about temperature and how temperature and volume are related. That's Charles' law. So that they should be able to explain that to me based on all the discussions and the simple gas laws that we've learned. And then how does particle motion relate to temperature and pressure? So that's kind of explaining in your own words how that's Charles' law and Gay-Lussac's law, how all of those things relate to each other and would relate to volume as well. But if I increase the temperature, what happens to the pressure? So the idea of getting how the gas particles, as they move, they exert pressure by collisions with the container. So I guess that's not Charles' law because there's no volume there, but Gay-Lussac's law. So again, getting into like how should we diagrammatically represent gas samples? Okay, that's kind of the big idea that we're trying to get at with these 3 questions. And so it says written explanation, but maybe I should add, they should draw a diagram, I guess. Yeah, I should add that to the slide. And then of course you should be able to prove to me that you have quantitative reasoning. And so specifically we would be reasoning around the simple gas laws and what I call condition changes. If I change the pressure, what happens to the temperature? If I change the volume, what happens to the pressure? Things like that. So we could do calculations, you could make graphs, you could write for every statements. Students should be able to demonstrate their understanding in all of those ways, okay? So regarding the simple gas laws, the combined gas law, and the ideal gas law. So that is my project. I hope you guys enjoyed it. I kind of talked really fast. Sorry, and at the same cadence. I guess I need to work on that. My principal says I just talk fast and I didn't pause a lot. My apologies. But yeah, if I'm not in the class, feel free to email me. Scott, you can share my email if you guys just even trivial questions or seemingly trivial comments about this. I would appreciate the feedback. Yeah, I've super enjoyed this class and hope you enjoyed the project. And I hope I didn't fail. Thanks, everyone.